Let us start with Newton's law of gravitation. Suppose we have two bodies with masses m1 and m2 kept at a distance r between them. This law states that the force will be proportional to the product of masses, that is m1 and m2, and the force will be inversely proportional to the distance square. Therefore, I can say that force is proportional to m1 m2 by r square, which in turn F is equals to G m1 m2 by r square. Now here what is G? G is universal gravitational constant. The value of this universal gravitational constant is 6.67 into 10 to the power minus 11, and the unit is very important. This is Newton meter square per kg square. This is the value and the unit of G, which is universal gravitational constant. Now the force will be acting towards this line, that is the line joining the masses. Now suppose the masses are in a coordinate system. Let the coordinate system be in this fashion. Let mass m1 is here, this is m1, r1 vector, and m2 is at this position, this is r2 vector. And the distance between m1 and m2 is denoted by the vector r vector. Let the force be denoted in this direction. This is the force. Now force will be the force on m2 by m1. So from our Newton's law of gravitation, I can say that force will be G m1 m2 divided by r square and minus r cap. Why minus r cap? Because it is in the opposite direction to r vector, and r cap here is the unit vector. Therefore I can also write r cap as r vector by r. From here I can say that the force F, this is equals to minus G m1 m2 by r cube, and here r vector, I have replaced r cap with r vector by r. Now I can also say that this r vector is nothing but r2 minus r1. Definitely in coordinate system I can say this. Finally I can say that our force F, this is equals to minus G m1 m2 by r2 minus r1 whole cube, and here r2 vector minus r1 vector. This is our force in vector form. Now the next question arises is, what is gravity? In the previous slide we saw that Newton's law of gravitation states that gravitation is a force between two bodies. Now if one body is our earth, then this force of gravitation is nothing but gravity. Hence gravity is the force by which earth will attract the body towards its center. Therefore I can say that gravitation, or rather gravity, is a special case for gravitation. Now here are some cases in which we need to find out how to write the force. Now the first case is to find the force between two point masses. As we have discussed already, the force between 2 point masses of mass m1 and m2 kept at a distance r between them is nothing but F equals to G m1 m2 by r square. The second case is a modernized case where there are two spherical bodies. Now here also the masses are m1 and m2, distance between them is r. I can assume the spherical bodies to be point masses and write the force as F is equals to G m1 m2 by r square. The third case is between a spherical body and a point mass, masses being same as m1 m2 and the distance being r. Here also I can assume the spherical body to be point mass and same formula, F is equals to G m1 m2 by r square. this can be used. Now this case is between a point mass and a rod. Now in case of a rod, I need to perform an integration because from the center of the rod the masses are different. Therefore we need to use F is equals to G m1 m2 by r square. This is not valid over in this case. I should take a strip of mass from this rod, find dm, and then I need to integrate the mass G dm into the point mass m2, and the distance will be x being the distance from the point mass. So I need to integrate from the initial position to the final position. The final position will be the length of the rod, and the initial position I can take it as 0. Then we will perform integration, which we will do in the further slide. Next we need to know what is the acceleration due to gravity. Suppose the mass of the earth is taken to be capital M and its radius is r. So applying the Newton's law of gravitation, I can say that the force F is equals to G m by capital R square. This small m is the mass of the object around which the force will act. Now using Newton's second law of motion, I can say that mg, this is equals to G mm by r square. So therefore G, this is equals to Gm by r square. Now this G is the acceleration due to gravity. Note that this G is independent of the mass of the object. Therefore if two bodies of different masses are allowed to fall freely, they will have the same acceleration. The value of this acceleration close to the earth's surface is 9.8 meter per second square. Now we move on to the variation of gravity. The value of G varies from place to place on the surface of the earth. It also varies as you go above or below the surface of the earth. Let us see how. For height above the surface of the earth, let us take this as our earth with mass m, radius r, and here is our object with mass m and it is at height h above the surface of the earth. So I can say that the force due to gravity is F is equals to G mm r plus h whole square. From here I can say that the value of gravity, I am doing it as G dash, this is a new gravity, so this will be force by the mass of the object, so this is Gm by r plus h whole square. Therefore G dash equals to Gm r square 1 plus h by r whole square. So I can write it as G by 1 plus h by r whole square, because you already know G equals to Gm by r square. So we have written G dash equals to G 1 plus h by r whole square. This is how gravity varies if you go above the surface of the earth. Now this can also be written as G dash equals to G of, I can put the denominator above like this. Therefore G dash equals to G of 1 minus 2h by r. But note that this formula can only be used if h is much less than capital R. We did this by using binomial approximation. Now let us see what happens if we go below the surface of the earth. So let this be our earth. We have gone to this position, mass of this object is m, and it has gone at a depth equals to d, and the radius of the earth is capital R, mass of earth is m. So now we need to calculate the mass of the sphere, the inside sphere to which the object has gone. So I can say that m dash, this equals to mass of the earth by volume of the earth. Let us assume that the earth is a sphere, so 4 by 3 pi r cube, this is the volume of the earth. This multiplied by the volume of the remaining portion, that will be 4 by 3 pi capital R minus d whole cube. So this will be the volume of the remaining portion. So I can write this as m dash equals to r minus d whole cube by r cube into m. So our force will turn out to be F equals to G m dash mass of object m divided by r minus d whole square. I can write it as G capital M small m r minus d divided by r cube. And finally, therefore, g dash equals to f by m. So from here I can say g dash equals to g 1 minus d by r. This is after we put all the values. If we try to summarize how the value of g varies if we go above or below the surface of the earth, I can say that for r less than equals to capital R, g dash equals to g 1 minus d by r. So I can write it as gr by capital R, where r minus d, this is equals to r. So from here I can say that g dash is proportional to r, and for values of r greater than equals to capital R, I can say that g dash equals to g 1 plus d by r whole square. This is equals to g r square by r square. Here r plus d, this is equals to our small r. So in other words, I can say that g dash is inversely proportional to r square. And if we draw the graph on how the value of g depends, I can say that, suppose this is our graph, this is r equals to capital R, I can say that it is directly proportional to r, g dash is proportional to r, and the value is g when r is equals to r, and it is inversely proportional to r square. So the graph will be like this: g dash proportional to 1 by r square. The value of g also varies with the axial rotation of the earth. So let us see how the value of g depends on rotation of the earth. So let our earth be like this, and it is revolving about its center, which is C, with omega. Let r be the radius of the earth. So I can say that here a force r omega square is acting, and g is acting along this diagonal, and this is an angle theta. Thus effective acceleration g dash is the resultant of g and r omega square. So g dash will be along this direction, g dash. Now the true acceleration g is acting towards the center C of the earth. So the effective acceleration I can write as g dash, this is equals to under root g square plus r omega square whole square plus 2g r omega square cos, the angle between these two resultant is 180 minus theta. So the angle between r omega square and g is 180 minus theta. So therefore I can write g dash equals to under root g square plus r square omega to the power 4 minus 2g r omega square cos theta. Now the term r square omega to the power 4 is very small, because omega is 2 pi by t, and 2 pi by 24 into 3600, this is a very small term, so I can ignore it. So ultimately I will get g dash equals to g square minus 2g r omega square cos square theta, power is 1 by 2. So this can be written as g 1 minus 2r omega square cos square theta divided by g 1 by 2. Again, using binomial expansion, I can write it as g 1 minus r omega square cos square theta by g. So finally what we get is g dash equals to g minus r omega square cos square theta. This is our final expression, and by using this expression I can say how the value of g depends on the axial rotation of the earth. So now I can say that Suppose let me take at the equator. At the equator, our G effective, which is G dash, this is equals to G minus omega square r, because our theta is simply 0 degree. And at the poles I can write, at the poles, G dash equals to G, because theta is equals to 90 degree. So at the poles the value of G is maximum, and at the equator the value of G is minimum, and the value of omega square r, this is equals to 0.034 radians per second, and this value is true for Earth. So let us learn about gravitational field and field strength. The space around a mass in which any other test mass experiences a gravitational force is called gravitational field. The vector quantity called gravitational field strength or intensity of gravitational field is denoted by the symbol E. So I can say that the gravitational field is nothing but it is the force experienced by a unit test mass placed at a point in a gravitational field. This is called the gravitational field strength, and it is denoted by the symbol E. So I can say E equals to F by M. This is our gravitational field or the field strength. So the SI unit of E will be Newton per kg. Now let us draw the field lines. Let us take mass as M, and the field lines will be in this direction. Now suppose that I have a test mass. Test mass is m naught. So what will be the force? The force this test mass will experience is m naught into g. G will be the field strength. So and this is the force due to capital M. Now let us see a few cases to determine the gravitational field strength. So let us start with a ring. So I have a ring over here, and let us take the important points. This is the center C of the ring. Let M be the mass of the ring and radius r. Let me denote this point as point P. It is at x distance. This angle be theta. Now in order to determine the gravitational field, I need to take elements. So let us take a small element over here, and the mass of this small element be dm. So certainly in this direction a field will act, which is dg. So if I break this component, vertical component will be dg sin theta, and this component towards the center, this is dg cos theta. Now I can also say that if this is capital R, so I can say r square, this is equals to x square plus r square, where small r is this distance. Basic Pythagoras theorem. Now let us solve. First of all, in order to calculate the gravitational field strength gx, this is integration of dg cos theta. I am neglecting the sine component because the vertical component sine theta will get cancelled if I take a similar element at the vertically opposite point. So dg sine theta will definitely get cancelled, and what is left is only dg cos theta. So this turns out to be g dm cos theta by r square. I can write this as g dm by r square, and for cos theta I can write it as x by r. So this turns out to be g x by x square plus r square 3 by 2, and integration of dm is left. So ultimately I will get this as g, and integration of dm will be m. So g mx x square plus r square 3 by 2. So this is our field strength for a ring at a point P. Now if we try to replace this to a graph, I can say that suppose this is the graph axis, This is x-axis, and this denote gravitation constant, I mean the field strength. So the graph will be like this, with peaks at, this peak will be at minus r by root 2, and this peak will be at r by root 2. You can easily differentiate this function and equate it to 0 to find the point where they will occur maxima and minima. So this will be the graph. So this will be the gravitational field strength for a ring. Now we need to determine the gravitational field strength for a long wire. For this infinitely long wire, let us assume this is lambda. What is lambda? This is unit mass. So unit is kg per meter. So let us take this point. This is at a distance r, and I need to find the field strength G. So G will be 2g lambda by small r. Now let us take the situation for a thin spherical shell. Let us name the points. This is the center of the shell. This point be A and this point be B. So the A point is definitely for small r less than the radius of the shell, and B point is for r greater than equals to the radius of the shell. So for the two cases, let me write the gravitational field for this case will be G equals to 0. For the inside the thin spherical shell, the field strength is 0, and for outside this is minus Gm by r square. If I try to draw the graph, for small r equals to r, this is G axis and this is the r axis. This is 0, r equals to r. From there, it is inversely proportional to r square. So in this fashion, and this value is minus Gm by capital R square. This is the field strength for both the cases for a thin spherical shell. Now let us see the gravitational field strength for a solid sphere. Before that, let me mark the point. This is center, this point is A, and this point is B. Let the inside portion of the solid sphere be mass n dash, and these distances are. So point A, this is for small r less than capital R. R is radius of the solid sphere. For this surface, the gravitational field strength, we need to calculate m dash. So m dash is mass m divided by volume of the sphere, which is 4 by 3 pi r cube, into the mass of the inside portion, which is 4 by 3 pi small r cube. So this turns out to be m r cube by capital R cube. Therefore I can say that the gravitational field strength G, this is equals to minus G m dash divided by r square, putting the value of m dash minus G m r divided by r cube. So this is the field strength for r which is less than the radius of the sphere. Now let us see for point B. Point B is for r greater than equals to the radius of the sphere. For this point, the gravitational field strength G is equals to minus Gm by r square. Now let us try to plot them in the graph shown below. This is G axis, and let this be the r axis. This point is r equals to capital R. So it is directly proportional to r, and it is negative, so the slope is in this fashion. And if r is greater than equals to capital R, it is inversely proportional to r square. So the graph is in this way, and here the gravitational field strength is minus Gm by capital R whole square. So this is the gravitational field strength for both r greater than equals to capital R and for r which is less than the radius of the solid sphere. Let us see what is potential energy. For this, let us draw a ball. This is a ball of mass m1, and we have another ball over here. This is a ball of mass m2. Now ball m2 is placed at a distance r tends to infinity. Now this mass m2 has to be placed in this position. So this is m2 over here. So initial position is r tends to infinity position, and this will be our final position. So we need to see what is the work done. Work done W equals to integration from infinity. The distance between m1 and the final position is r. This is r. So integration from infinity to r, g m1 m2 by r square dr. So this will turn out to be minus g m1 m2 divided by r. This is the work done. Now we know that the work done W equals to change in potential energy delta U. So this is W equals to U final minus U initial. So I can write this implies minus G M1 M2 by R. This is equals to U final minus U initial is 0. Why? Because we know that at infinity the potential, which is U, this is taken to be 0. U equals to 0 at infinity. Therefore, I can say that U final equals to minus G M1 M2 by R. So this is the potential at a point for a given mass at a position R. Gravitational potential. Gravitational potential at any point is defined as the negative of work done by gravitational force in moving a unit test mass from infinity where potential is assumed to be 0 to that point. Here I am taking the point as P. Thus potential at P is Vp equals to minus of work done from infinity to that point P divided by the test mass, and the SI unit of potential is joule per kg. Next we will discuss how to write the gravitational potential for different situations. Let us start with the point mass. So let us assume this is a point mass m, and we need to find the potential at this point P, which is at a distance r. So the potential here is V equals to minus Gm by r. Now let us write the potential for a ring. For this ring, let this be the radius r of the ring. This point is P, which is at a distance x, and this is r. In order to write the potential, we will use a similar technique. We will take small elements. This small element mass is dm. Now dv, small potential, will be minus g dm by r. So v equals to minus g by r integration of dm. So v turns out to be minus gm divided by, and small r was r square plus x square from Pythagoras theorem. So r square plus x square 1 by 2. This is the potential for a point P for a ring. If we try to draw the graph will be in this way. This is the x-axis, this is potential v-axis, and this minima will be minus gm by r. Next, let us write the potential due to spherical shell. This spherical shell is of mass m, radius r. This is the center of the shell. This point is A and this point is B. For point A, this point is for r less than r. Potential V equals to minus Gm by r. For point B, this point is for r greater than equals to capital R. V equals to minus Gm by small r. Now if we plot this in a graph, up to r equals to capital R, the V is constant, potential equals to minus Gm by capital R. After that it varies inversely with r, so inversely proportional to r. So this will be the graph. Now for any point outside, we can assume that all the mass is situated at the center C, and hence we can write the potential for a spherical shell. Next we write the potential due to a solid sphere. The mass of the sphere be m, radius r. This is the center of the sphere C. This point is A and this point is B. So point A, for r less than the radius r of the sphere, V potential equals to minus Gm by 2r cube bracket 3r square minus small r square. This is the potential for any inside point where r is the radius of that point, and for point B, which is for r greater than equals to r, V equals to minus Gm by small r. Now if we try to draw this in a graph, So this graph will be a parabolic curve. So this point is minus 3 gm by 2r, and for r equals to r, the potential is minus gm by r. After that, it is inversely proportional to r. So this will be the graph. Now for any outside point, we can assume that all the mass is situated at the center. Hence we can write the potential for that point. Next we will learn about the relation between gravitational field and potential. In gravitational field, field strength E and potential V are different at different points. So they are functions of position. So I can say that E and V are functions of three variables, three Cartesian coordinates x, y and z. Further, E and V are not independent functions, but they're related to each other. How they're related? They're related by differentiation or integration. We will learn about this in the next slide. So conversion of V function into E function. To convert V function into E function, we need to perform differentiation. So differentiation is required. So I can write E equals to minus, this is del V by del X I cap, plus del V by del Y j cap, plus del V by del Z k cap. Now what is del V by del X? This is called the partial differentiation of V with respect to X. Similarly, the others are the partial differentiation with respect to Y and respect to Z respectively. So if there is only one variable, E equals to minus dV by dx. Now we need to convert E function into V function. Now to convert E function to V function, definitely I will use integration. So integration will be required in this case. So I can write dV, this is equals to minus E dot dr. So I am integrating dV from A to B equals to minus integration A to B E dot dr. So VB minus VA, this is equals to minus integration of A to B E dot dr. So if there is only one variable, I can say that dV, integration of dV, this is equals to minus integration of E dot dr or dx, depending on what coordinate I have used. Next we will see what is escape velocity. I am denoting it with VE. This is the minimum velocity so that this small mass escapes planet's gravitational pull. So this is mass M, capital M, radius R, mass of Earth. This is center C. This small mass is small m. It will go with velocity VE, the escape velocity, which we need to find. So this is the initial position, and finally it will go to infinity, because at infinity the g of planet will be taken as 0. So here velocity v equals to 0, final position. Now we will use energy conservation. Kinetic energy initial plus potential energy initial equals to kinetic energy final plus potential energy final. Kinetic energy initial half m VE square. Potential energy initial is minus g mm by r. This is equals to 0 plus 0, because kinetic energy and potential energy both are 0 at infinity. So from here I can say VE, this is equals to under root 2 gm by r. This is approximately equals to 11.2 km per second at Earth's surface. Orbital velocity. We know that the necessary centripetal force to the satellite is being provided by the gravitational force exerted by the Earth on the satellite. Thus, F equals to mv0 square by r, which implies gmm by r square equals to mv0 square by r. So v0, which is the orbital velocity, this is equals to under root gm by r. So v0 is proportional to 1 by root r. Hence the orbital speed of the satellite decreases as the orbital radius of the satellite increases. We can also write the orbital speed of a satellite close to the Earth's surface is v0 equals to under root gm by capital R, radius of the Earth. This is equals to under root gr. This is equals to VE. VE is the escape velocity, VE by root 2. So after substituting VE equals to 11.2 km per second, V naught turns out to be 7.9 km per second. Next, we will discuss about the energy of satellites. The potential energy of the system is U equals to minus G mm by R. The kinetic energy of the satellite is K equals to half m V naught square. This is equals to half m Gm by R. So K equals to half G mm by R. The total energy will be summation of the kinetic and the potential energy. So total energy E equals to K plus U equals to minus G mm by 2R. So E equals to minus G mm by 2R. This energy is constant and negative, which implies that the system is closed. Farther the satellite from the Earth, greater will be its total energy. If we try to plot them in this graph, this is the R-axis. This will be the kinetic energy, positive, and both the potential and the total energy is negative. So E equals to K plus U. And binding energy BE equals to minus E. This is equals to G mm by 2R. The binding energy is the energy required to be given so that the small mass m escapes. So let us discuss about Kepler's laws of planetary motion. Kepler, which is the scientist's name, he discovered 3 empirical laws that accurately describe the motion of the planets. The 3 laws can be stated as: the first law is the law of elliptical orbits. Each planet moves in an elliptical orbit with the sun at one focus of the ellipse. We know that the body is acted on by an attractive force proportional to 1 by r square. So the only possible closed orbits will be a circle or an ellipse. It was shown that the orbits under the attractive force F is equals to k by r to the power n are stable for n less than 3. Therefore, it follows that circular orbits will be stable for a force varying inversely as the distance or the square of the distance. The second law is the law of areas. For this, we need to draw an ellipse. This S is the position where the sun lies. This is the focus of the ellipse. This is point P and it moves to point P dash. So P dash equals to V dt. So P dash M, this is equals to P dash sine theta equals to V sine theta dt. In a small time interval dt, the line from the sun S to the planet P turns through an angle d theta. So the area swept out in this time interval is small area dA. dA equals to the area of the triangle. So this is half base into height. So half SP into P dash M equals to half R V sin theta dt. Therefore, the aerial velocity dA by dt equals to half RV sin theta. Now what is RV sin theta? RV sin theta is the magnitude of the vector product R cross V. So this is 1 by m times the angular momentum L. So L is R cross mv. So ultimately we will get dA by dt equals to 1 by 2m modulus of R cross mv. So this is equals to L by 2m. So dA by dt equals to L by 2m, which is a constant. Thus Kepler's second law, that aerial velocity is constant, means that angular momentum is constant. The second law is actually the law of conservation of angular momentum. The third law is the law of time periods. It states that t square is proportional to r cube. Newton was able to show that the same relationship holds for an elliptical orbit with the orbit radius r replaced by the semi-major axis a. Thus, t equals to 2 pi a 3 by 2 divided by under root g ms. Here ms is the mass of the sun. As we have come to the end of this chapter, let us discuss about some paths along with their projected velocities. If v equals to 0, we will get path 1, which is a straight line. If v from 0 to v0, where v0 is orbital velocity, we will get path 2, which is a elliptical path. If v equals to v0, we will get path 3. When it is equals to orbital velocity, we will get path 3, which is circular. when our v is between v0 and escape velocity, we will get path 4. This is also elliptical, but this ellipse is having a greater semi-major axis. If v equals to the escape velocity, we will get path 5, which is a parabola. This is path 5. And finally, if our v is greater than the escape velocity, we will get path 6, and this is a hyperbola. Let us conclude this chapter by discussing about the double mass system. Here we can see that two masses m1 and m2 are revolving about their common center of mass, which is C. This center of mass C, this is called the barycenter. Now if this is R1, this is R2, R1 plus R2, this is equals to R, and we know how to calculate R1 and R2. R1 equals to M2R by M1 plus M2, and if we need R2, R2 will be M1R divided by M1 plus M2. Now things to be noted here is that both M1 and M2 will have the same time period and omega. And what is this common omega? This is omega equals to under root G M1 plus M2 divided by R cube. This is the same angular velocity which they will rotate with. And the second thing is V1 by V2. This is omega R1 by omega R2, same omega, which is equals to R1 by R2. These are two important relations about the double mass system, and hence we conclude the chapter gravitation.